Nothing about spiders is normal. Here's why. A single strand catches the light. Thinner than a human hair, invisible until the sun hits it at exactly the right angle, and suspended at its center, motionless. Wait, something that has been perfecting its craft for 400 million years. We think we know spiders. 8 legs, webs and corners, the occasional shriek when one appears in the bathtub. But what we think we know, it barely scratches the surface of what these creatures actually are. Because spiders are not simple. They are not primitive. And they are certainly not normal. They are older than trees, older than flowers, older than dinosaurs. By nearly 200 million years, they existed before anything we would recognize as a forest, hunting across landscapes of moss and fern, in a world without birdsong, without color as we understand it, without any of the life forms we consider dominant today. And in that immense span of time, they developed abilities that should not exist in something this small. Silk stronger than steel, venom that rewrites nervous systems, eyes that work like telescopes, legs powered by hydraulic pressure rather than muscle. The deeper you look into how spiders actually function, the stranger they become. Not strange in the way of alien worlds or science fiction, but strange in the way of something that evolved right beside us, in every corner and crevice of the planet, perfecting systems we are only now beginning to understand. This is the hidden engineering of spiders, and nothing about it is normal. To understand what spiders are, we first need to understand what they are not. They are not insects. Calling a spider an insect is like calling a whale a fish. The error is that fundamental. Spiders belong to an ancient lineage called collaterals, creatures that split from the insect line over 500 million years ago, back when complex life was still experimenting with basic body plans. Their closest living relatives might surprise you. Scorpions, horseshoe crabs, even ticks. These are their distant cousins, all descendants of marine ancestors that made the long transition from ocean to land. In the dim prehistory of our world, insects developed 6 legs, compound eyes, antennae, and eventually wings. But the collateral lineage went somewhere else entirely. 8 legs, 2 body segments, no antennae, no compound eyes in most species. Instead, simple eye clusters and something far more sophisticated, thousands upon thousands of sensory hairs covering every surface of their bodies, reading the world through vibration and touch. And here is something most people never consider. Spiders evolved before flowers existed, before bees, before butterflies, before the colorful ecosystems we associate with nature today. They were among the first complex predators on land, hunting in a world of ferns and mosses and enormous arthropod prey, landscapes we would barely recognize. Some of the earliest spider fossils, like Idmonarachne from around 305 million years ago, show features that no longer exist. Segmented plates on the abdomen, possibly a short tail. These were evolutionary prototypes, experimental designs, nature testing what would work. Most of those early experiments failed. The fossil record is littered with spider lineages that vanished, body plans that led nowhere, designs that could not compete with what came next. But what truly set spiders on their path to dominance was not their legs or their body structure. It was two revolutionary inventions that changed everything: venom and silk. Venom is one of evolution's most elegant solutions to a fundamental problem. How do you safely kill something that might kill you first? But here is what surprised me when I started researching spider venom. It did not originally evolve for killing. It evolved for digestion. Early spiders had digestive enzymes in their gut, like most animals do. But at some point, those enzymes began to be produced in glands near the fangs instead. When injected into prey, these enzymes started breaking down tissue externally, pre-digesting the meal before it was even consumed. Think about that for a moment. Digestion that happens outside the body, the prey becomes the stomach over millions of years. Some of these enzymes mutated into something far more dangerous: neurotoxins. Instead of just dissolving tissue, they started disrupting nerve signals, paralyzing prey almost instantly. This gave spiders an enormous advantage. They could subdue dangerous prey without prolonged struggle, without risk of injury. And venom did not just evolve once. It evolved independently in multiple spider lineages, each time producing different chemical cocktails tailored to specific prey. Tarantulas developed venom optimized for insects and small vertebrates. Widow spiders evolved neurotoxins that target the nervous systems of larger animals, including us. Funnel web spiders in Australia produce some of the most potent venom on Earth. Compounds that can kill a human in hours if untreated. And here is a detail that makes the funnel web even more unsettling. Its extreme toxicity to humans is completely accidental. Dogs and cats bitten by funnel webs experience mild irritation at worst. But primates, our sodium ion channels happen to share the exact molecular shape as insect calcium channels, a coincidence of biochemistry that makes their venom devastatingly effective against us. We were never the target. We just happened to be collateral damage. But here's something that might unsettle you further. Most spider venom is not designed to kill. It is designed to liquefy. Spiders are external digesters. They bite, inject venom loaded with digestive enzymes, and then wait. Wait for their prey's insides to dissolve, to transform into a nutrient-rich soup that they can simply drink. Some species have evolved venom that works like anesthetic, numbing prey tissue so the victim cannot struggle while digestion begins. Others use compounds that hijack muscle control entirely, forcing prey into paralysis while keeping it alive. Fresh food, stored for later consumption. This is predation at a chemical level. Warfare waged through molecular precision. And it set the stage for the next great innovation. Silk. If venom was the spider's weapon, silk became its superpower. Spider silk is one of the most remarkable materials in nature. Pound for pound, it is stronger than steel. It is more elastic than rubber, stretching up to 40% of its length without breaking. And spiders have been producing it for over 380 million years. But silk did not begin as a web-building material. Its original purpose was far simpler. Protecting eggs, early spiders produced silk from specialized abdominal glands called spinnerets, wrapping their eggs in protective cocoons to shield them from predators and the elements. Over vast stretches of time, they discovered other applications. Drag lines as safety tethers when climbing, burrow linings for underground homes, and eventually aerial snares. But here's where it becomes extraordinary. Modern spiders do not produce just one type of silk. They produce up to 7 different kinds, each with distinct properties, each manufactured for a specific purpose. Dragline silk, the strongest variety, forms the framework of webs and serves as the spider's lifeline. Capture silk comes coated in sticky microscopic droplets, designed to trap prey on contact. Wrapping silk immobilizes victims, bundling them securely for storage. Attachment silk bonds threads to surfaces. Egg sac. Silk protects offspring. Each type comes from a different gland, and spiders switch between them effortlessly, depending on the task at hand. The golden orb weaver produces silk that glows gold in sunlight, a shimmering thread that seems almost supernatural. Darwin's bark spider manufactures silk tougher than Kevlar, building webs that span rivers, some stretching over 25 meters, the largest orb webs ever recorded. But not all spiders use silk for webs. Bolus spiders spin single threads with sticky balls at the end, swinging them like lassos to catch moths in mid-flight. Some even release pheromones that mimic female moths, luring males directly into their trap. Water spiders construct diving bells, underwater air chambers made entirely of silk, allowing them to live beneath the surface for hours. And then there are the balloonists, spiders that release long strands into the wind, riding air currents to travel hundreds of kilometers, some crossing entire oceans. We call it ballooning, but what they are really doing is flying. Yet perhaps the most incredible thing about spider silk is not its material properties. It is how spiders use it as an extension of their own nervous system. A spider's web is not just a trap. This is what changed my understanding of these creatures entirely. A web is a sensory organ. When prey lands on a web, vibrations travel through the silk strands like signals through a fiber optic network, and spiders read these vibrations with extraordinary precision. They can identify prey species just from the frequency of the vibration. They can estimate size from movement amplitude. They can distinguish between struggling prey, mating signals from potential partners, and simple interference from wind. Some can even detect the difference between a moth and a beetle before they ever leave the center of their web. Silk transmits vibrations with incredible efficiency. Each strand acts like a tuned guitar string, resonating at specific frequencies. Spiders monitor the entire structure simultaneously, either from the center or through dedicated signal threads that run to their hiding spots. Research has shown that orb-weaving spiders can detect and locate prey in complete darkness, using only vibrational information. Different web designs optimize for different kinds of intelligence gathering. Orb webs excel at detecting flying insects. Funnel webs amplify ground vibrations. Cobwebs confuse prey while providing multiple signal pathways. And here's something that surprised me deeply. Many orb weavers rebuild their webs every single day. They tear down the old structure at dawn, consume the silk to recycle the proteins, reclaiming roughly 90% of their investment, and then construct an entirely fresh web optimized for current conditions, humidity, wind direction, recent prey activity, all factored into each new design. The web is not permanent architecture. It is disposable technology, a sensory interface rebuilt daily to maximize hunting efficiency. This is extended cognition made physical, a way of perceiving the environment that the spider's nervous system alone could never achieve. The web becomes part of the spider's mind. But the web is only half the story. The spider's body contains engineering just as extreme. Most spiders possess 8 eyes, arranged in patterns that vary between species, each eye serving a different function. But jumping spiders, they develop something truly extraordinary: telescopic vision. Their large front-facing eyes contain layered retinas that move internally, scanning the environment without requiring any head movement. They perceive depth through a mechanism called chromatic aberration. Different wavelengths of light focusing at different distances within the eye. They can see ultraviolet light, wavelengths completely invisible to human perception. They can track movement with precision that rivals cats. And they do all of this with eyes smaller than the head of a pin. This visual system gives jumping spiders hunting abilities that seem almost impossible. They pursue prey without webs, pouncing from distances up to 50 times their own body length, landing with pinpoint accuracy. But that explosive leap, it reveals another bizarre adaptation. Spiders do not have extensor muscles in their legs. Let that sink in for a moment. They cannot straighten their legs using muscle power. Instead, they use hydraulics. They pump hemolymph, their equivalent of blood, into their legs, creating internal pressure that forces joints to extend. It is the same principle as construction equipment, pistons, and hydraulic fluid, but miniaturized and biological. This system provides incredible jumping power, but it creates a critical vulnerability. A punctured exoskeleton means loss of pressure, which means the leg cannot extend properly. This is why dying spiders curl up. The hydraulic system fails, and the legs fold inward. Beyond vision and locomotion, thousands of specialized hairs called trichobothria cover every spider's body. These hairs are so sensitive they can detect air movements as small as 1/10 the width of a human hair. Some species use them to sense insect wing beats before prey even touches the web. Others detect air displacement from approaching predators, providing precious milliseconds of warning. One study found that certain spider hairs respond to sound wave frequencies. effectively allowing spiders to hear without ears. Mechanical deflection of sensory structures converted directly into perception. Everything about spider physiology seems optimized, refined through hundreds of millions of years of evolutionary pressure into something approaching biological perfection. But it is their hunting behaviors where things become genuinely unsettling. Trapdoor spiders construct hidden burrows with camouflage lids, waiting motionless, sometimes for hours, before launching ambushes so fast they are difficult to capture on high-speed cameras. The strike takes less than 1/10 of a second. The prey never sees it coming. Net-casting spiders suspend themselves above forest paths, holding rectangular silk nets in their front legs, and throw them over passing prey in complete darkness. They have evolved enormous eyes that gather light with such efficiency they can hunt on moonless nights. Crab spiders change color over days to match the flowers they hunt on, becoming invisible to the pollinators they consume. The transformation is slow but precise. Ant-mimicking spiders disguise themselves so perfectly, walk in patterns, chemical signatures, body shape, that they infiltrate ant colonies, hunting workers from within. And then there are the social spiders, species that defy everything we assume about spider behavior, living in colonies of thousands, sharing webs, raising young cooperatively, hunting in coordinated groups. They are rare, but they exist, challenging our understanding of what these creatures can become. But perhaps the most surprising discovery is not the diversity of strategies. It is evidence that some spiders can plan. Spiders have tiny brains. Most of their nervous system fits inside their cephalothorax, with room to spare. A jumping spider's brain is roughly the size of a poppy seed, and yet jumping spiders of the genus Portia demonstrate behaviors that look remarkably like planning. When hunting other spiders, which is dangerous prey that fights back, Portia spiders perform reconnaissance. They observe target webs from a distance, sometimes for extended periods, analyzing structure and the position of their prey. Then they execute detours, approaching from angles that minimize detection, even when this means temporarily losing sight of the target. This suggests spatial memory and route planning, cognitive abilities we typically associate with vertebrates, with animals that have brains thousands of times larger. So what is happening inside a brain the size of a poppy seed that enables this? One hypothesis suggests that spider cognition is heavily embodied. Intelligence is not centralized in brains processing abstract information, but distributed across sensory systems, directly coupling perception to action in ways we do not fully understand. Webs become part of cognitive architecture. Hydraulic legs provide real-time feedback. Sensitive hairs create tactile maps of the environment that update constantly. Spider intelligence might not work like ours at all. It might be a form of cognition that we do not yet have the frameworks to comprehend. And evolution has not stopped. It is happening now in every spider population on Earth. Urbanization is creating new selective pressures. Some spider species have adapted to artificial lighting, building webs near lamps that attract concentrated insect prey. Others have shifted their activity patterns entirely, avoiding light pollution by hunting during different hours. There is growing evidence that some species have evolved to live almost exclusively indoors. Synanthropic spiders thriving in human structures, hunting household pests. Populations genetically isolated from their outdoor relatives, potentially undergoing speciation right now in the houses and buildings we occupy. Climate change is driving rain shifts. As global temperatures rise, spider species are expanding into territories that were previously too cold. Tropical species moving into temperate zones, creating new predator-prey dynamics, new competition, new ecological relationships we have never observed before. And through all of this, spiders persist. There are over 45,000 known species today on every continent except Antarctica. They occupy deserts and rainforests, mountains and coastlines, caves and canopies. Some live at altitudes above 6,000 meters. Others thrive in complete darkness underground. Wherever there is prey, there are spiders hunting it. They survived the Permian extinction, the greatest die-off in Earth's history, when 90% of all species vanished. They outlived the dinosaurs. They endured ice ages, supervolcano eruptions, asteroid impacts, continental drift, the rise and fall of countless dominant species, 400 million years and counting. Whatever happens next, whatever changes the planet undergoes, whatever new challenges evolution presents, they will likely still be here long after we are gone, waiting, watching, perfecting their craft in the shadows, as they always have. We share this world with ancient engineers, creatures whose silk and venom reshaped entire ecosystems. whose tiny bodies contain hydraulic systems and distributed intelligence, whose webs function as external nervous systems, reading vibrations we cannot perceive. They are not simple, they are not primitive, and they are not what we thought they were. The next time you see a web catching morning light or notice movement in the corner of the room, remember what you are looking at. 400 million years of refinement, watching you, reading every vibration just as carefully as you are watching it. But spiders, they evolved to dominate the land, the open air, the hidden spaces of the terrestrial world. There is another realm entirely where evolution took a very different path, a place with no life, pressures that would crush steel, temperatures that swing from freezing to boiling within meters, and creatures shaped by forces so extreme that the deeper you descend, the less they resemble anything from our world, the deep ocean where light cannot reach, where life becomes something else entirely, and where the question is not what lives down there, but why. The deeper you go, everything gets stranger and stranger and stranger. Why deep sea creatures get creepier the deeper you go.